Hello class, this is CSE-5250, Section 60, Week 1, Fall 2023, and welcome to Parallel Programming. I'm the instructor, Giovanni Orijuela, and this is an asynchronous version of an in-person class that I teach on campus. So, as this is an asynchronous class, there are no Zoom meetings that you have to attend. Instead, I just post the videos online for you to watch in your own time and for you to follow along. The one disadvantage of this format is there isn't as much student-to-teacher interaction. But if there is one advantage to this, it's the fact that you can just rewind the footage to where you need it to be and just watch it again if you feel like you need clarification on any part. So yeah, you can basically rewind the video to whatever point you need to as you need it. So that's one advantage that this async format has had. So, as I said, welcome to Parallel Programming. This video is going to be divided into 3 chapters. The first 2 is basically an introduction to the class itself. More specifically, the first chapter of this video. And chapter in the sense of YouTube chapters, like how you can divide a video into specific sections. The first chapter is gonna be a bit about myself. The second chapter is gonna be what we're gonna be doing for the rest of the semester, and the third chapter is going to be why do we care about parallel programming. So, I usually begin the course with a question of how I got here. How I got to where I am. There are 2 answers to these questions, and I always answer it using the most literal interpretation of the question. How did I get here physically? This question does not have the same weight as it would compared to if this were a in-person class. But the answer that I would traditionally give is I just drove north on the 215, exited on University Parkway, parked my car in the parking lot, walked over to the classroom, and that's it. That's how I would get here. Of course, I'm at my home right now, so it doesn't really work the same. But I've since turned that answer on its head by taking the train instead. There's several reasons as to why I started taking the train. One of which is I hate traffic jams. Yeah, so that's one reason. The other reason is there's a parking garage there's a parking lot garage at one of the stations. So I just leave my car there to charge. Because my car is electric, I leave my car at the parking garage to charge, take the train, transfer to the SPX green line at the other station. So I take the train from this parking garage to San Bernardino downtown station. I then transfer to the SBX green line and just ride the bus the rest of the way to Cal State San Bernardino. Sometimes I wonder what it would take to have a physical rail connection between San Bernardino downtown to CSUSB. That would be really neat, but at the same time, where do you put it? But anyway, neither answer to the question of how I would get here, neither taking the car nor train doesn't really answer the question of how I got here. Really, how I got here is a chain of events that extends about 10 years, roughly 10 years back. 10 years and change. So, early 2010s, I knew for a while that whatever occupation I wanted to get into, it would have to involve computers. I spent so much time staring at a glowing rectangle that maybe I may as well turn it into a job. So, early 2010s, I started attending community college, and 2016, that's when I got my associate's degree in computer science, and I was ready. I was rearing myself to transfer to UC Riverside. So what made me choose Cal State San Bernardino over UCR? Well, it has to do with the commute. You see, at the time, I was living pretty far away in a pretty rural area in California. And to go to either campus, either way, no matter which campus I had chosen, it would have involved at least a 90-minute commute. That if you were to account for that, Google Maps would report that such a commute would take about 100 minutes. That isn't accounting for breaks or traffic jams. So, typically, these days, if I'm to make the same journey, I say it's about 2 hours. So a 2-hour commute. And I have to drive all the way there. But we found a way to get there, and I don't have to drive as far. So it turns out that both campuses have a satellite campus called Palm Desert Campus. But the thing is, Cal State San Bernardino has a shuttle that goes between the satellite campus and the main campus. So, in terms of reducing commute times, it was basically a no-brainer for me to choose San Bernardino over what was actually my first option. UCR was my first option. So, this paradoxically made my commute longer, so instead of a 90-mile commute, it was something more like 140, because there is a section of the commute where it is a backtrack. But it has the clear advantage of I don't have to drive the entirety of that commute. I only have to drive like about half. Half of that commute is me driving, but the other half is me relaxing on the shuttle. So yeah, that's actually the first link in the chain of how I got here. The second link was around 2017, 2018, and I thought to myself, what if I instead dual majored in both computer science and game development? So at the same time I was taking community college classes, I was also hooked on a video game that basically was my first experience in software development. It was a game that is at least 20 years old now. It is a game called SimCity 4. It is a city simulator. And modifying that game, I was part of a team that modified the game's road systems. That was my first experience in. That was the closest experience I had to game development at the time. And more broadly, my closest experience to software development. So, I figured I could use. Initially, I thought I could use that experience to find some job in the world that had to do with computer science. But then maybe because I had so many other skills unrelated to computer science, like art, I figured maybe I can dual major. And so I did exactly that. I had to submit a form that says, hey, I'm changing my major from computer science to computer science and game development. So fast forward to 2019, 2020, I finally did it. I got my degrees in both, I got my bachelor's degree in both computer science and game development. But then I had another thought to myself. What if I went for a master's degree in computer science? And so, I made that decision. This is the third link in the chain. And then, COVID happened. Yeah, I made that decision right before the pandemic began. Right before we had all of our quarantines, lockdowns, and Zoom meetings, and realizations that we need to have robust internet connections to attend class. So yeah, 2020 was not only the start of the pandemic, but also the start of me pursuing my master's degree. So I was taking classes related to, taking classes required for my master's degree. And 2022, right on the beginning of 2022, was when the CSE department reached out and asked me to teach. So that was how I got to where I am now, teaching some of the very classes that I had to take as either an undergrad or a postgrad. So that is an experience in and of itself. And mirroring what one of my professors had said to me, the best way to learn is to teach. Because as you teach what you had learned, you learn more about what you thought you knew already. So that is how I got to where I am now. That's me. This is a summary of my education. Bachelor of Science, Computer Science, and Game Development, 2020. And my still in progress, but one day, possibly soon, Master of Science in Computer Science. Oh, we have a textbook. Introduction to Parallel Programming by Peter S. Pacheco and Matthew Malinsak. ISBN 9780-1280-46050. So, get this textbook as soon as you can, because even though we won't be needing it eventually you will be doing programming exercises from the book. So, by around week 3 is that's perhaps the earliest. That's perhaps the soonest we'll be starting to use the textbook for, well, programming. Parallel programming. Let's go over that syllabus. So, CSE 5250, Parallel Algorithms and Programming. As I said, I'm the instructor, Giovanni Orijuela. Email is actually the best way to contact me, but in the past I've had students request a Zoom meeting between the two of us, so although it isn't explicitly stated in the syllabus, you can, if you need to, request a Zoom meeting with me. We would have to arrange a time, of course, and then I'd have to give you the Zoom link. But if you have any sort of matter that cannot be easily answered via email, we can organize and schedule a Zoom meeting. As I said, this is an online async course, but here are the prereqs. CSE 4010, or what used to be 401 under the quarter system. Topics include algorithm design, analysis, and programming of high-performance computers, control parallel versus data parallel approaches, and selected parallel programming languages. This used to be known as CSE-525 under the quarter system. So here's the grading scale. Well, we're mainly going to be looking at programming assignments. I have details regarding the midterm and final, and there's a fourth category of assignments that I refer to as short answer questions. This is the main way I take attendance, actually. So here's a tentative schedule of what is to happen for the entire course. The first day of class was actually August 24th, but that was a Thursday, so there was no Monday, Wednesday classes on that week. So for our purposes, I'm gonna call that week 0. So instead of this being week 2, this is week 1. Because this would awkwardly make fall semester 16 weeks instead of the typical 15 weeks. That's because of how Thanksgiving break takes one day away from the week. And to compensate for that, the semester had to begin on Thursday, August 24th. We do have a day off upcoming, and that is September 4th. So that is already next week. I will still put up a video on that week. It is all async after all, but the first 2 chapters in the book, it's basically why parallel programming and what kind of hardware do we have for that. It's around the 3rd week that we're gonna start to do actual programming. So I'm actually going a bit out of order in the book, and that's because OpenMP, I am really comfortable with working with OpenMP, so I feel like that's the one I would teach the first, but then we're gonna look at pthreads after that. Followed by that, MPI and CUDA, because we're gonna be looking at 4 different APIs as described in this book. Oh yeah. You have a midterm and final, but they're not exams, they are projects. I'm gonna have you try 2 of the APIs to write a program. You're gonna be writing a program with those 2 APIs. But you're actually gonna be writing a 3rd program that's gonna be part of both. And that is you're gonna be writing a program without any parallelization, and then you're gonna rewrite the same program using 2 of these APIs. Using one of these APIs is OpenMP, and the OpenMP rewrite of that program is gonna be your midterm. The rewrite using MPI is gonna be your final, but you're actually not just gonna be programming you're not just submitting the program, you're also submitting benchmarks. I'll get more in depth about the benchmarks, but basically, when the hope is, we have this hope regarding parallel programming, and that if we were to rewrite a specific program from serial to parallel, that it would grant us some sort of speed boost. That's the hope. In practice, we're gonna practice seeing what happens when you try that. So the benchmarks are your midterm and final. We also have parallel programming exercises. Again, I'm gonna be using the textbook for that. So that actually covers 3 of the 4 categories of assignments. The last one is what I call short answer questions. If I am to ask this to you, you basically have 1 week for you to answer that question and submit an answer. You are to submit this answer on Canvas, by the way. In fact, everything's gonna be submitted through Canvas. Oh, please be sure to submit your work on time. I know that when you need it the most, your internet connection can vanish. Or worse, your internet connection could go out more than you do. So, just in case that happens, if you have an assignment that is up to 1 week late, I will still take it. However, anything later than that will require a reasonable excuse as to why it's late. This syllabus is actually incorrect. What it should include is a late policy regarding the midterm and final. So I'm actually going to be enforcing a late policy regarding the midterm and final. It must be on time. Unless you have made arrangements with me ahead of time to account for a late submission, or you have evidence for an extenuating circumstance. So in short, there is a 1 week grace period for all assignments except for the midterm and final. So I have to include this in the syllabus. I'll be updating the syllabus later on to account for that. So yeah. Academic policies, you refer to academic regulations and procedures in the CSE-USB bulletin for courses. Academic honesty, don't cheat, and don't use ChatGPT to do all the work for you. You could ask ChatGPT for help regarding debugging, but don't use ChatGPT to cheat. You are allowed, however, and encouraged to discuss the material related to assignments with each other, but all the assignments in this course are to be individual work. So, no cheating, no exchanging of solutions. You can help each other out with with getting things to work. And if cheating were to take place and you get caught, at best you're gonna get a grade of a 0. At worst, you're gonna face expulsion. When it comes to the attention of a student that possibly dishonest behavior took place, that student should report it to the instructor. Adding and dropping a class. The policies can be found at this link here, under the adding classes and drops and withdrawals headers. And students to services to students with disabilities, SSD. If you're in need of an accommodation for a disability in order to participate in the class, please contact me and SSD. It's the student's responsibility to seek academic accommodations for a verified disability in a timely manner. So that's the syllabus. So with that, I'm going to switch gears to the third part of this video, and that is, why do we care about parallel programming? This is chapter 1 in the textbook, so it summarizes why do we care and what can we do. Why do we care and what can we do? Why do we care? Why do we care about parallel programming? Can't we just wait for CPU technology to advance? Why build parallel systems in the first place? And even if we do need these kinds of things, can't we just make a program that can automatically parallelize our programs? Well, here's why we should care. Up until the 2000s, CPU performance basically doubled every 18 to 24 months. Moore's Law. It's technically not a law in the sense of how Newton's laws of motion are laws. Rather, it's an observation, but an observation that held up for a good while up until the 2000s. So, CPU performance basically doubled roughly every 18 to 24 months. So, if you wanted a more powerful computer, all you had to do was wait for one to hit the market. But that trend has long since ended. Starting around the 2000s, we hit a wall with trying to increase computer performance. So instead of something like 50%, it went down to like 4%. So the only way around it... So I'll get into why we had to go down this route, but by 2005, CPU manufacturers started to produce multi-core CPUs, starting with the dual cores, and the core count only went up from there. Meanwhile, the kinds of computer problems that need more powerful computers have increased. So, climate modeling, protein folding, folding at home is one such example of protein folding. Drug research, energy research, data analysis, the kinds of things related to big data. You need a really powerful neural network, but you can't just use your old desktop computer from 2005 to do anything like that. You would need way more processing power than that. So, why we're building parallel systems. So what happened? There are several different ways to measure Moore's Law, and if we were to go by clock speed, for example, clock speed was increasing at a predictable rate, but it stopped. Why? Because these suckers get hot. Okay, so there are different ways of measuring Moore's Law, and another metric of doing so is size of the transistors. We don't really use that anymore for technical reasons. Nowadays, if you hear 7 nanometer whatever, that's more of a marketing thing. But it more or less describes the size of the transistors on the integrated circuit itself. More or less. So if you're going to measure Moore's Law by transistor size, they too were shrinking at a predictable rate. And then that stopped. But the biggest advantage of shrinking transistors over the years, you can get more processing power for the same amount of energy. More speed. There's one big disadvantage, however. by making us, if you want a CPU to run faster, you need to increase its power consumption. But the thing is, a CPU also outputs waste heat. So if you have more transistors in the same area, you have more transistors putting out more heat. And our air-based cooling systems for our computers have long since reached its limit too. There are even more limits than this, by the way. One, for example, is quantum tunneling. So the transistors have two states, 0 and 1, on or off, but electrons can quantum tunnel and randomly flip these bits from 0 to 1, and oops, now your simulation has crashed. Randomly, too. We used to use clock speed as the only metric to indicate that a computer was fast. Nowadays, another typo. Clock speed. We've only just reached 5 gigahertz within the past few years. For the longest time, it was basically plateaued around 2, 3, 4 gigahertz. That's 2, 3, or 4 billion clock cycles per second. It's only recently that we started to have CPUs that had more than 4 cores be so commonplace that you could just buy a multi-core CPU. If we're not including server or workstation CPUs, the highest core count CPUs available now, those suckers have 16 CPU cores. That is epic. Actually, no. Epic is AMD's server CPUs, and those go up to 64 cores, from what I understand. Intel's server CPUs, those are Xeons. They also have core counts that are around that count as well. Also, CPU clock speed is no longer the only metric regarding performance. We also have instructions per clock cycle, because we had to find ways of executing more instructions in the same amount of time. And without parallelism, even without parallelism, there is one other way of extracting more performance. It's called pipelining. I have an analogy for pipelining in the presentation later on. But if you've heard of like, there's like a pair of security vulnerabilities regarding pipelining. So, but even without those vulnerabilities, pipelining does have a few disadvantages. I have one related to this. If you've ever gone to one of those automatic car washes, make sure if your car has a feature called auto hold, where it will hold its position, you may, just in case, you may need to turn it off, because if you do, you will stall that car wash. You'll stall the pipeline, as they say. Ask me how I know. I actually stalled an entire car wash once. So that was fun. So why do we need to write parallel programs? Most programs that were written for single-core systems cannot use more than one core. Yeah, you can run multiple instances of the same program, but that doesn't help. SimCity, one of my top favorite games of all time, that is single-core. And unless we can somehow find the source code for that, or possibly make an open source rewrite of the entire game that can take advantage of multiple cores, there is no way we can turn a single core program into something that can utilize more than one core. In the absolute worst case, that source code could be lost forever. But assuming you're lucky and you do have the source code, how could we parallelize it then? Well, there are two ways. The hope is we can somehow write a program that can parallelize the code for us, or we have to do it the hard way and write it ourselves. So as it turns out, researchers have found very little success in writing such converter programs. Even in cases where certain operations can be parallelized, the resulting code may be slower. So at worst, basically, if an algorithm works in a specific way and a converter program were to parallelize it, it might parallelize it in a way that might be worse for the performance of the program. So at worst, we would have to redesign our algorithms. We would have to redesign our algorithms for that. So how do we do that? Well, turns out there's two kinds of parallel programs. How we write parallel programs depends on how the work is partitioned between multiple cores. You can have task parallelism, where different tasks are divvied up between multiple CPU cores, or data parallelism, where it's the same task, but it's the same task being executed on each core, but they have a workload so big that it's divided amongst those cores. So that's data parallelism. Okay, so here's the analogy I was talking about. This includes pipelining. Imagine you had to wash multiple loads of laundry because, I don't know, you were backed up on laundry one day and now you have a huge pile of laundry that you now need to wash. You could wash one load at a time. But let's say your laundry machines, you cannot run both of them at the same time. Say the circuit breaker will trip if you had to run both at the same time, or one of the outlets is broken or whatever. Let's just say you can only operate one laundry machine at a time. Say you can only run the washer but not the dryer. You would have to wash one load and then dry that load and then fold that load. And then you'd have to load the next load. Wash that. Then dry that and then fold that. This is obviously slow. But it's also not an efficient use of our time. So let's say you fix the wiring in your house, and now you are able to run both the washing machine and the dryer at the same time. So here's another solution. You wash the first load. When that's done washing, you load that into the dryer, and at the same time, as that's drying, you load the second load. When the second load is done washing, when the second load is done being washed, and the first load is done being dried, you take out the first load from the dryer, so you can fold that, you move the second load from the washing machine to the dryer, and then you start the third load in the washing machine. So this is actually an analogy on pipelining. So this is a 3-step pipeline. Wash, dry, fold. So at any given time, you're doing 3 batches of laundry at once. They're just in different stages of the wash, dry, fold process. This also assumes that we are devoting the same amount of time to each operation. In my experience, I have never had the washing machine and dryer complete the same task at the same time. It always felt like the drying step took more time than just the washing step. And maybe that is true. And if so, you're going to have to account for that. It means the washing machine might have some time where it's idle before it means the washing machine is going to have some idle time but before you are able to move loads between machines. There is another solution. Give up and go to a laundromat. Once there, you can divide your laundry between multiple machines, and you can run all of them at the same time. Of course, then after, you can have a situation where you have 5 loads of laundry finishing at the same time, and then you might have to move each one by one to 5 separate dryers, and then wait for those to dry. And then, unless you have brought helpers with you to help fold laundry, you're gonna have a pretty large folding session. So that's one thing. So that's one consideration regarding parallelism. But the textbook also has a different analogy. Here's the textbook's example. A professor is teaching a 100-student class, and there are 4 TAs helping her out. The professor gives out a test, and the test has 5 questions on it. How do they grade all 100 tests? The textbook gives 2 solutions to that. The TAs and the professor each grade a separate question. In total, each person will have graded 100 questions each, but each will have graded a different question. That's solution 1, and it turns out that it's an analogy to task parallelism. Each of the graders is given they're all given the task of grading a question, but they're all grading different questions. The other solution is data parallelism. Divide the pile of 100 exams to grade into 5 piles of 20. Each grader gets a pile to grade. It's the same number of questions being graded, but each grader will have graded all the same questions. There are considerations to either of these approaches. For example, you gotta make sure everything's divided, because if in the absolute worst case, one grader has 96 tests to grade and the others have only 1, that's a waste of time. Speaking of time, some graders may finish faster than the others. Now what? So there are several things to consider. One of them is communication. In solution 1, you have to send one single test to 5 different graders. The thing where the scenario that I mentioned where one grader has 96 exams to grade and the others have 1, that is an extreme example of what happens when you don't have load balancing. But again, that assumes that all 5 graders can grade at the same speed, given the same amount of work. Synchronization. What if in solution 1, one grader is faster at grading a specific question? What if in solution 2, one grader finishes first, even with load balancing? In my pipelining example with the laundry machines, I mentioned how it feels like it takes longer to dry than it is to wash. In the pipelining example with the 2 machines, it means that the washing machine will sit idly with a load full of wet laundry, while the dryer is still in the middle of a drying session. That means somewhere in the pipeline, some step in the process has to wait until it is able to proceed with proceeding to the next thing. So eventually you will be looking at 4 different APIs: OpenMP, POSIX threads, MPI, and CUDA. And we can classify these in 2 ways: how they share memory and the number of independent data streams they can handle. So the textbook describes 2 such things, but it turns out there are 5 ways, 5 classifications of data stream count and process count. And here is all of them. If we have a single data stream and 1 process, that is SISD. So every program that we have ever written, possibly every program you have ever written to date, there's a good chance that it's all serial programs, which for the purpose of this class is boring. What if we had a what about single instruction, multiple data? That's the same instruction, but on different data. That's data parallelism. One instruction stream working with multiple pieces of data at once. Multiple instructions, single data, multiple programs working on the same data. So imagine if you had to do data analysis on one big data set and you're doing all sorts of calculations on the same data set. Say you had to find the standard deviation, but you also want to find the mean, the median, the average. Then there's MIMD, multiple instruction, multiple data. Different instruction streams each working with different data. There is a 5th category. There's also a 5th category. SPMD, single program, multiple data. Copies of a single program allowed to execute different parts of its codes on different data. So these 4 APIs will fall into some of these categories, but the textbook only describes 2 such categories actually. Those categories are SIMD, single instruction, multiple data. Some of the APIs fall under that category. The other one is MIMD, multiple instruction, multiple data. Some of our APIs will fall under that category. SPMD is a kind of overlap between the 2. And so, we have reached the end of our first presentation. The next chapter in the book is going to be about parallel hardware, parallel software. It's going to be a review on the von Neumann architecture and what changes we've had to do to that to make parallel programs work. So yeah. What kind of special hardware do we need to execute parallel programs? I will say this. If you have built your computer within the last couple years, there's a good chance that you already have hardware that can execute certain parallel programs already. If I can just use my computer as an example, bam. This is an 8-core 16-thread CPU. I wanted to put a 16-core 32-thread CPU in this monster. I feel like this computer is a bit of a monster. What you're not seeing is the fact that my computer has 3 screens on it. But I had issues with trying to install a Ryzen 9 into my computer. It didn't work. I tried it a few different ways. I had it brought to Best Buy. They suspected it could be a manufacturing defect, so I'm sorry, I don't have I, I wish I could show you a 16 core 32 thread CPU operating on my computer, but it just didn't happen. It was a Ryzen 9 5950X, so if it isn't a manufacturing defect, then it's probably the fact that the two are just I have a B350 motherboard in my computer, so I think it's the fact that it is so old and the 5950X so new, and it's preventing the two from working with one another and resulting in BSODs. So maybe instead I'll just go straight to the 7950X. That'd be insane, but I guess that's for me what makes building my own computers so fun, but also risky. Oh well. That's gonna be it for the first video. If you have any questions, email me, let me know. And I'll see you next week.